So first thing you want to notice is how for a particular solid, or sorry, for a particular liquid, well, first of all, what are the axes? So temperature, and then this axis represents vapor pressure. So at a certain temperature, and if we go back to this diagram, you remember that some of the liquid evaporates and forms a certain amount of vapor pressure in that container. So this is quantitatively what vapor pressure each of these liquids would have at different temperatures. So for example, at 20 degrees Celsius, chloroform would have a vapor pressure of about 23, and the units would be kPa. Okay, and then as it gets warmer, its vapor pressure increases. So the reason for that is this graph. Okay, so this is why as you get higher temperatures, a greater portion of the total has the minimum Ke to evaporate, and therefore the vapor pressure increases. Okay, so we can see there's a couple things we need to note about this graph. One is as temp increases for any liquid, like we can see that trend is true for all of these, vapor pressure increases. Okay. Another thing we can do with this graph is compare the vapor pressure of multiple liquids at the same temperature, for example, 60 degrees. So at 60 degrees, chloroform has a vapor pressure that is basically equal to atmospheric pressure. It's about 101 kPa. Ethanol's vapor pressure at this temperature is about 50. Water's vapor pressure is about 23. And ethanoic acid's vapor pressure is about whatever that is, 15. Okay, so this trend that it goes that like some have higher vapor pressures than others at the same temperature is explained by this graph. Okay, so we can see that they all have the same curve, which means they're all at the same temperature, but different amounts of energy is required for each one to evaporate, which means different portions of the total amount of liquid will evaporate and contribute to the vapor pressure. So it's those two graphs again that we come back to and over again that are at play here. So another observation is that at the same temp, different liquids will have different vapor pressures because it's the big question. Okay, so when we think about what we talked about before, the strength of something's IMFs dictates how much energy, dictates like where this line is, okay? How much energy is required for it to evaporate. So the stronger the IMFs, the more energy is required to overcome them, which means less evaporates. Really weak IMFs means very little energy, relatively, is required to overcome the IMFs, and a greater portion of the sample will evaporate. So if we look over here, then we can see that because at this given temperature, ethanoic has the lowest vapor pressure, that must mean it has the strongest IMFs. Conversely, chloroform, which has the highest vapor pressure at this temp, has the weakest IMFs, and then water and ethanol fall in between. And that makes sense too. We understand that ethanols are higher than waters for reasons we've talked about, so it makes sense that that's supported by this graph. Okay, so back to point 2 here. At the same time, different liquids will have different vapor pressures because they have different IMFs. Well, different strength of IMFs. And then we could add to that and say stronger IMFs, and this is review, leads to lower vapor pressure. Okay, so another important thing to note here is that eventually, when something gets warm enough, it'll boil. So if we look at water, we know that there's an important data point for water, which is that at 100 degrees Celsius, it starts to boil. Okay, and if we take that point all the way up here, we can see that at 100 degrees Celsius, water's vapor pressure is actually equal to this dashed line. And if we go over to the left here, we see that this dashed line is just above 100, and we can see here also 101.3 kPa, which is the same as 1 atmosphere. So we can see that when water's vapor pressure becomes the same as the atmospheric pressure, it will start to boil. Okay, so that leads to an important point here, which is the second one here. Like when the vapor pressure, which was the y-axis on that graph, equals atmospheric pressure, which is either 101.3 kPa or 1 atmosphere or 760 millimeters of mercury, you get boiling. Okay, the y for that is it continues to elude me a little bit, but the best thing that I have found is that you can think of it as like the liquid trying to evaporate is like pushing, the liquid trying to evaporate, quote unquote trying to evaporate, is pushing up, right, and the atmosphere is pushing down. So at some point, that pushing is equal. Like the atmosphere is pushing down as much as the liquid is the vapor, while the liquid trying to become a vapor is pushing up. And at that point, you have basically boiling happening. Whereas evaporation was just at the surface, the boiling starts to happen all through the liquid at that point. And that's where there's like a qualitative change from evaporation to boiling. So we would say boiling only happens when the vapor pressure equals the atmospheric pressure and happens throughout the liquid rather than just at the surface. I'll read that again. Boiling only happens when the vapor pressure is equal to the atmospheric pressure, whereas evaporation happens at all temperatures that it's a liquid. And boiling happens throughout the liquid, not just at the surface, and you guys can verify that from your personal experience, that you can see the bubbles forming all through the liquid, like in a pot, and when we make the rock candy, you'll see that again. Okay, so an important point to notice then is that water does boil at 100 degrees. That's what we always say up here. However, it doesn't only boil at 100 degrees. So in Los Altos, where the pressure is about 1 atmosphere, we would say that yes, it boils at about 100 degrees. And we have a little asterisk here there because that's called the normal boiling point. So when we talk about water boiling at 100 degrees, that's when it normally boils, which is to say the boiling point when the atmospheric pressure is equal to 1 atmosphere. Okay, so the normal boiling point is the boiling point when the atmospheric pressure is equal to 1 atmosphere, and that's normally what we talk about. We say, oh, ethanol boils at this temperature and water at this temperature. Speaking of ethanol, we can actually use that graph to figure out ethanol's normal boiling point. So we want to see at what temperature, right, at what temperature does its vapor pressure match, that's not quite right. We want to see at what temperature its vapor pressure matches atmospheric pressure, so that's about here. So if we take that down, we can see that its normal boiling point is about 78 degrees. So this graph can help us figure out the normal boiling point of all these things. Okay, so let's see, we can find the normal boiling point of all these things. Like this one we could take straight down and find it, and this one we could take straight down and find it. And again, it makes sense that because things with stronger IMFs, their vapor pressure builds more slowly, it's going to take a higher temperature for them to boil. So we can also extrapolate that idea from this then, that, or actually let's just do it like this. Substances with stronger IMFs lead to lower vapor pressures and therefore higher boiling points, because it takes more heat for the vapor pressure to build up until it matches the atmospheric pressure up here. Okay, so okay, so let's head back down here. So then let's talk about not normal boiling points. So in Tahoe, where the pressure, the atmospheric pressure is 0.84 atmospheres, what temperature would water boil at? So we're looking for the temperature. It's not going to be 100 degrees. So when the vapor pressure, I'm going to do a different color here. When the atmospheric pressure in Tahoe is about 0.84, so that's like maybe here. That means that the vapor pressure of the water does not have to build up as high in order to match atmospheric pressure, because atmospheric gets so much less, right? So we can extrapolate down here then to find the approximate boiling point of water. So if this is maybe 90, maybe it's like 94 degrees. Okay, so water boils a little bit cooler in Tahoe. Okay, and then if we look at Everest, it's even more extreme. Okay, so I'll do that one in a different color. Everest, okay, so its atmospheric pressure is 0.34, so maybe around here somewhere. It's like a third of what we experience, which is why it's hard to breathe. There's about a third less oxygen. I mean, there's about a third of the oxygen, about 2/3 less. Okay, so if we go down here, water would boil at about 70 degrees, which is insane. So 70-degree water is not very hot. So the weird thing about that is if you tried to boil water to make like tea or coffee and you're on top of Everest, it would boil when it felt lukewarm. And this is actually a demo that I can do for you if we ever go back to school. Where you can boil water and like you can remove so much atmospheric pressure that it actually boils at a relatively low temperature and doesn't even feel hot while it's boiling. So and the last takeaway then is you can determine the boiling point at other pressures by looking at this table, okay? At this graph. All right, that's a lot for 2 slides. Okay.